Today in this video, we're going to be looking at frequency distributions. This whole unit is going to be on summarizing and graphing data, finding ways to present data so that it's understandable, more easily analyzed by people. And today's topic is this one, frequency distributions, which is a way of organizing your information so that it's easier to see any trends that are going on with the data. And there's actually a lot of other things that we can more easily analyze when it's in a frequency distribution. When you talk about data, the numbers, you have to understand that the characteristics of data change. The characteristics are things like the mean, median, and mode. Okay, there's terms you should know. The range, that would be something you may or may not know. Things like that, though, those are the characteristics of data. So, for example, in 1905, approximately, 8% of homes had a telephone. Well, that definitely went through some changes. 14% of homes, and notice this is a mean, an average, this is a mean. The number of homes with bathtubs, the mean was 14%. Hopefully that one has changed. The mean life expectancy was 47 years old. The mean hourly wage was 22 cents an hour. And in 1905, there was around 250 murders in the entire United States. And so I'm showing you this to give you the idea that, yeah, as time goes on, the characteristics, and all of these, I'm just giving means. And we didn't do the modes, we didn't do the range, or there's lots of other things we could discuss here. But these are just the means, but hopefully you recognize that the means here have all changed. I've got actually a graph about the murders here. And 1905 is right about in here. And I don't really know what happened in that period of time, but you'll notice that there was quite a drastic jump. I did a little research once because I was so curious, what in the world happened in that particular period of time. There was a big influx of immigrants. Big influx of immigrants coming into the United States from Europe right about in here. And so it's not necessarily that those people were committing more murders percentage-wise. It's that, if there's more people around, well, then there's probably bound to be a few more murders. As time goes on, it's an interesting one because you can see the mean here keeps changing. And again, then it went up, then it went down. And this here, this is a frequency distribution, actually, that you're looking at, classed by 1 year at a time. Okay, so and that'll make more sense to you later on what I mean by classed by 1 year at a time. We're just going by ones. But it's a frequency distribution, a count, and so you can see how frequently something was happening. And when you have like this, very easily we can start to ask questions about things. Why did it take a dip in this area here? Why did it start to go back up after that dip? It wasn't necessarily because there were fewer people, even though after World War II there were fewer people. Maybe that's what it was. So there's questions that you can start to develop by looking at frequency distributions. So when we're going to take a look at frequency distributions, usually it has to do with the fact that we've got a bunch of data and we want to analyze it. I've got some data points here, and actually not a ton of them, but these are the actual high temperatures between September 1st and October 5th. So 80 on October 1st, 77 on October 2nd, 81 on September's. I mean the September's here. September 1st, 2nd, 3rd, 4th, 5th, so on and so forth. And here's another row, and here's another row. And when it was just one row, you could sort of get a sense for what was going on. It's like, well, mostly 70s and 80s it looks like. But you start to add more rows, and there's a 60. Okay, so it's starting to maybe you can say it's starting to cool down because the 60 showed up. And then of course you get into the third one here. Well, they got some more 60s showing up. So you could probably argue that there's a trend of getting from warmer to colder. That would be probably about as far as your analysis is going to take you just by looking at that. And I would say this, if I hadn't scrolled through and shown you one at a time, and just showed you all three at one shot, it'd be very overwhelming to try and analyze it just by looking at it. And that's the whole point. When you just have numbers, it can be difficult. People are good at up to about 10, maybe 15 digits, not digits, excuse me, numbers. But you get past that, and people have a hard time comprehending what they're looking at. If this was, say, 500 data points, you would really, really struggle to make any sense out of it at all, because it appears to be so random to most of us. So the characteristics, the mean, the median, the mode, the range, things like that, the variance, which I know that's another term that you don't know what it means yet, but we'll go through it. The characteristics, very difficult when it's just data. So what we do, we try to arrange them. The first step typically is we will arrange them into groups. Those groups are called classes. And you can decide what the width is in each group. That murders one I mentioned, the width was only 1 year. But I could have gone by 5-year increments. In this particular one, I'm going by fives. Now you got to be careful when you look at these. This is called the class, okay? This is a class, this is a class, this is a class. You might look at it and say, well, there's 4. Well, we're not looking at subtracting. You have to count 55, 55, 56, 57, 58, 59. So there's 5 numbers covered in this particular class. How many numbers? That's referred to as the class width. So this one has a class width of 5. So I am going by 5s here. And when it's like this, you can see trends much, much easier. You say, hey, there was only one day that was really getting hot. There was a lot of days that were in the mid 70s to mid 80s. Only one day that was really cool. Just becomes much easier to start to analyze your information. Now there's other things we can't do with this one. I actually don't know what the coldest temperature was. You might speculate that it was 55, but I don't know that. All I know is we had one day between 55 and 59. One day between 85 and 89. So I can't answer all the questions I would ask here, but I could start to answer some of them. If I said, hey, what do you think the mean temperature was? Again, that implies an average. The mean temperature, well, probably in this area somewhere in here would be where you would find the average, the mean temperature. When we talk about characteristics, these are what I'm referring to, the center. And that's sort of a vague term when I say the center, because it could mean different things. Representation of the average values that indicate where the middle of the data set is located. Okay, so I'm going to try to explain right now why we don't use the term average a ton in statistics. Because the average, when you think average, you're thinking add them all up and divide by how many there are. But it's actually a description of the center, which the center can be described with the mean, with the median, or with the mode. So it's not a specific term. It's kind of a general term, where mean, median, and mode are very specific. So the center, we typically want to know about where was the middle of our data. Again in here, I haven't actually crunched any numbers, but my guess is, well, the center is somewhere in that area there. It's kind of growing, and then it's going down. Maybe it's up here just a little bit. Variation is really just the short version of that is, hey, how spread out is the information? Definition variation, is this a measure of the amount that the data values vary? But if you were putting this in your notes, I'd put it in as how spread out is it? For example, if I was to take all the senior female students in the high school and find their average height. Okay, so I would end up with a shortest, I would end up with a tallest, and by range is what's in between. But if I changed it, instead of just being seniors, and I did every girl from kindergarten through the 12th grade, well then my shortest is going to change quite a bit. My tallest could be, maybe there's a really tall junior that doesn't get counted, but the shortest end of it definitely would change my data. So it would be way more spread out, and that's called the variation. From the center, how spread out is it? That's a way of looking at these two here. You've got a center, and then from there, how far up or down do you go? That's the variation. And we're going to have a couple of different ways of describing variation later on. The distribution. The distribution, we're going to be looking at different kinds of distributions. One of them, the main one that you're familiar with, I'm just going to kind of draw it here, is what's called the normal distribution. If you think about heights of students, again, let's just go back to the senior class, just the girls. Well, you're going to have a few short girls, okay? And you're going to have a few tall girls. And in the middle area, you're going to have a lot of girls that are kind of that average, that mean height, that average height. And so what you end up with is this shape that you probably know as the bell curve. But in statistics, we call it the normal curve. There's one kind of distribution. They don't have to be like that. Okay, there's other distributions, lots of kinds of distributions. If you say roll dice, just a single die, just take a single die and roll it 1,000 times. Well, you're going to get a certain number of ones, and you're going to get a certain number of twos, and it's going to approximately be the same. 3 is going to show up about the same number of times as the twos and the ones, and so on and so forth. And you're going to end up with kind of a square rectangular looking distribution, okay, for the 1, 2, 3, 4, 5, and 6. Most likely, you might get one that happens to show up a little bit more than the others, only because of randomness. But in general, it's going to be pretty flat. It's going to be different than height. So this is a kind of distribution. We have other distributions that maybe peak real soon and then sort of tail off. Or in the opposite direction, maybe we have ones that grow really slow, and then all of a sudden you get your most. And these are called skewed distributions. Okay, they're skewed. And there's certain things in life that tend to be like this. And we get into all of that. But those are distributions. A distribution is the nature or shape of the spread of the data over the range of values. Range is from lowest to highest. I don't care which distribution you're talking about. The range is lowest to highest. What's the difference between the lowest and the highest? Then we have what are called outliers. Once in a while you get a data point or maybe a couple that are just way, way out there. Maybe you've got this one here with the height of the girls, and there's some girl that's just really, really short, way out here someplace. Well, that's maybe an outlier. We actually have to go through and we calculate whether or not that's going to be far enough out that if it is an outlier, we tend to throw it out. But there's a calculation to know whether it's an outlier, and that actually has to do with making what's called a box and whisker plot, which you may have made those before. Sometimes that's taught in like an Algebra 1 class. But it's the idea of being very far away. But it is calculated. We can't just look at it and say, well, I think that's an outlier. We have to calculate that. We'll do that at a different lecture. So frequency distributions. Okay, so what we've got here, I've got some retirement ages. Okay, so this is really just a random set of data. I don't know that it's actual real set. I think I just made some numbers up here. So some retirement ages. Typically we want to sort them so it's easier to look at. And this type of analysis is almost always done with a spreadsheet. Excel, Google Sheets. Excel works very, very well. Google Sheets works decent. And so we're organizing. Then we'll make up our classes. And then we'll count how many times we have a class. So between the ages of 52 and 55, 3 people retired in that age class. So making those. So frequency for a particular class, the number of original values. So these are the originals. These are just sorted. So they're still considered the originals. They're just sorted. Fall into that class. Typically you want to sort, because like here, I can see really fast. Oh, I got 1, 2, 3, 60. So if I wanted to go from 60 to 63, I could, okay, that's starting there. It's going to there, and then I could just count. So if you have stuff, you want to sort it. By the way, you can do this in your graphing calculator. And what you do is you input your data, and then you're going to go to single variable stats, and you're going to say sort, and it'll sort it for you. And so you go back to where you inputted your data, and it'll be nicely arranged for you. So it's easy to do. But you can also do this with Google Sheets. You can do this with Excel. pretty much anything that's trying to analyze data will have a sorting option, because that's a pretty basic thing to do with statistics. Okay, lower class limit. They're the smallest numbers that it can belong to. So you look at your classes here. Well, they're the ones on the left. 52, 56, 60, and so on and so forth. So that for this particular one. And by the way, I picked the classes. When you set this up, you get to pick what do you want it to go from. They just need to be the same width. What that means is, so it goes 52 to 55. So if you count 52, 53, 54, 55, that's a class width of 4. 56, 57, 58, 59, that's class width of 4. Once you pick your width, then you can divvy up, you can divide up to get your classes. You actually choose your width first, is what you're going to do. But you got your lower limits, you got your upper limits, those are just the numbers on the right side. Then you've got your class boundaries. They're the numbers that go between where one ends and the next one starts. It's halfway between the gaps. So 55, 56. Let's say that we get into the months here. You know, somebody, let's use 2 months. 55 years old with 2 months past their birthday. Well, that's on the 55 side. If we know 6 months would be halfway. So 55 in 2 months, they would go into this class. But 55 in 10 months, well, then we would round up to this one. So class boundary is the number we use to separate the classes. It's halfway in between. So in this case, it'd be 55.5, which is the 0.5 would represent 6 months. The class midpoint. What you do, you take the low end, you take the high end, you add them together, and you divide by 2. Okay, so 52 plus 55 divided by 2, that would give you your class midpoint. Later on, we will be making what are called histograms. A histogram, you're going to at first say, well, that's just a chart with rectangles. And I've drawn a blank on the name right now. But anyways, you're going to say, well, that's just one of these kinds of charts. Well, histogram's a little bit different. And when we make the histogram, sorry, I couldn't find my mouse. There we go. When we make our histogram, we're going to have these rectangles. The placement of the rectangles is centered around the midpoint. That's the only reason we would ever need to really know the midpoint, is to know, okay, when I make this chart here, the rectangles need to be centered around that midpoint. So we'd have to find them. Now, when we actually make histograms, most of the time the computer is going to find it for us. So very rarely would you ever need to find a class midpoint. In the old days, when people did these things by hand, well, then yes, they needed to find them. The class width, this you'll need to know how to do. The idea of how wide is it? I already explained that the class width here, so 52, 53, 54, 55, has a width of 4. And what you're going to do to get that is, like I already mentioned, you will first decide how many classes do I want, because that's going to be this down here. Number of classes. How many do you want? And then you simply take the biggest value minus the smallest value. So you find the difference, and then you divide by the number of classes. Now, a lot of times you will end up with a decimal, and that's okay because you're going to do a little bit of rounding there. We usually round to some convenient number. Say it was ended up being 3.7. Well, then I'd say, well, let's just have a class with a 4. Or 5.1. Maybe I'd round down and say, well, let's have a class width of 5. And you would just understand that maybe one of your classes would end up a little bit bigger than one of your other classes. But typically it works out pretty well. You set these up. Something to be aware of, we will be making these both with a spreadsheet, whether you're using Google Sheets or Microsoft Excel. We'll also be making these with the graphing calculator. The graphing calculator is less user-friendly, not in the sense that it's harder to use. It's very easy to use, but it doesn't give you a choice of how many classes. It decides how many classes it wants to have. So in those cases, if you're in an assignment or on a test, if I tell you you need to use this many classes, you can't use your graphing calculator most likely because it chooses how many classes it wants to put it into. So it's a little bit frustrating in that sense because it's really easy to use, but it's easy because of the lack of choices you're given. With the spreadsheets, you're given more choices, but that of course means you have to tell it more information, which would, some people would say, well, that's harder because I have to tell it more things. Yeah, but you get more choices with it. So, and we'll be going through how to do that. I actually have a video for that stuff under topic 0. All right, so that's the frequency distribution. Then we get into what are called the relative frequency distributions. Relative frequency distributions basically is the idea of this. You take how often it happened in that class. So this is the same information here. Still my retirement stuff. Between 52 and 55, there was 3 people. I'm going to divide that by the total. There's your summation symbol. It means I added them up. So I just added these up. Here's 24, which would be the same number as if you added up how many were in this column. There should be 24, same as this column. So there's 24 data points. I'm going to divide the frequency by the number of data points. And I get this number right here. And you're already seeing something else. These two just kind of go together. We get our relative frequencies so that we can usually then get our percentage frequencies. They're considered 2 different things, but it's usually I'm getting these so that I can get these. And you can see here all this difference between this one and this one is I switched it from a decimal to a percent. So we've got our frequency distribution, we've got our relative frequency distribution, and we have a percentage distribution, which is the exact same as this one. It's just that there is percents instead of decimals. So you won't necessarily do any calculations over here. You'll just switch it to a percent. Here you'll do a calculation. Typically I like to do this with Excel, and if you used Excel, what I would do is I would put in the formula. I would say equals, and then I would click on this so it takes that 3, and I'd hit the divide symbol, and I'd hit this cell because I'd give my 20, so I want to have it go 3 divided by 24. And then if you've used Excel before, you can copy your formula. So I hit enter, it's going to boom, automatically give me this. And then if you've ever used Excel, you can bring your cursor over to the bottom right corner, and it looks like a big fat plus symbol. And you hold down your mouse and drag down, and it's copying the formula that you just did. So I wrote a formula. I said equals this divided by this. And then I copy it. So it does it for me. So a lot of this, I just let the computer do it for me. I'm not actually doing this by hand. In fact, then to here, I let this equal this one. I copy it again, and so I copy the formula because I'm actually writing a formula equals this one, but then I format these cells to show me a percentage. Okay, so it's really not as much work. Your most work is going to be entering your data. Once you've entered your data, this is really easy to do. It looks like a little funnel. It looks kind of like something like this. It's on the right hand side in Microsoft Excel. You would select, what I would do is I would copy the data, and then I would select it all, and I'd hit my little funnel, and it'll just sort it for me. I've got a whole video on how to set up the classes and have it count the frequencies, but even here, the computer is going to do the counting for you once you tell it what you want it to do. And then I do my little formulas to get my relative frequency, and I do my little formula and reformat to get my percentages. All right, so there I've kind of told you what I'm going to do. Relative frequency is just the class frequency, again, in this case is 3, divided by the sum of all frequencies. How many data points did you have? Percentage frequencies, I've pretty much explained that. It's really the same thing. You just multiply by 100. And even here, you're probably not doing this by hand. Well, what I just talked you through is probably what you'll do. You'll just do this in a spreadsheet. Let the spreadsheet do all the work for you. You just got to figure out how to use it. As a check right here, you should sum up your percentage frequencies. It should add up to 100%, because if it doesn't, that means you probably missed something somewhere. if you got 95%, you're missing a number. If somehow you got 103%, well, then somehow you had an extra data point. You'd want to check your work. But that would be the only reason for adding it up, just to make sure you didn't goof anything up. Then you have what are called cumulative frequency distributions. Cumulative frequency is, think about like when snow accumulates, it just keeps adding up on top of each other, adding up on top of each other. So notice my original frequency at the top was 3. And then I had another 3. 3 plus 3 is 6. And then I had a 9. 6 plus 9 is 15. And then a 4 and so on. I'm just adding them up as I go. If I was to put them together a graph of this, cumulative frequencies will generally look something like this. They're going to keep growing and growing and growing because you just keep adding the frequencies together. And there's a reason for some applications, we'll get into later when we're making graphs, why I would ever want to even do that. There are some applications for doing that. So that's called a cumulative frequency. And I didn't make a new chart, but you can do cumulative percentage frequencies, you can do cumulative relative frequencies. It just means I'm adding them up as I go. This one's just cumulative frequency. But anytime you see the term cumulative in front of some distribution, it tells you, hey, you're just going to keep adding them up as you go. And the numbers should keep getting bigger and bigger and bigger. Oops, I was going to make a comment here. Yes, your last number here should always equal how many data points you had. If it doesn't, then you missed a data point someplace. So that's just a little side note thing. Interpreting data. You're going to be asked to interpret data as you go through this. So here's some classes, and what we're talking about here is pulse rates. This one, there's women and there's men. And so what we would say here is that a pulse rate between 50 and 59, so that's how many beats per minute, 15% of men average, when we use that average, I don't know if that's mean, median, or mode, but they're averaging between 50 and 59. So let's just, it's probably a mean. So the mean number of men with that pulse rate is 15%. The percentage of men with a mean pulse rate in here is 42%. The percentage of men with a mean pulse rate here is, of course, 20%. And that's how you would want to read this. I find it interesting when you look at this that they're not the same. Believe it or not, men and women are different. When you look at this, though, you can start to ask some questions. Where is the center? Because the center for the women, that seems to be about in here somewhere. But the center for the men, that seems to be just looking at it more up in here somewhere. And I know these aren't tally marks, I know it's on a graph, but I can still, by looking at the percentage frequencies here, I can have an idea of where the center of the data might be. Is there a difference in variation? Again, variation is how spread out from the mean, okay, or from the lowest to the highest. And I would say, yeah, you know, if you look at it, the men's, it went from 50 to 99. So basically, let's round that off a little bit, basically 50. They had a range of 50 beats per minute. But women, they had, starting at 60 all the way up to, let's round a little bit here, about 130. That's 70. So the variation in women is much greater than the variation in men. That would be, I don't have numbers per se. I can just look at it and say, I can see that the variation is different. Later on, we'll talk about putting numbers with that. Is there a difference in the distribution of the data? Yeah, there is. We already mentioned that, okay, the men here, there's men with pulse rates this low, but there are no women with pulse rates this low. Then there's, up here, there's women with pulse rates this high, but there aren't men with pulse rates that high. There's also something kind of strange with the women's, is that there's a class here that there's nobody in there, and then it has a class above that. There's nothing like that with the men's. Once it goes to 0, it just stays 0. That's kind of an interesting thing. Is there an outlier? This actually is not an outlier if you actually do the calculation. If you just look at it, it might seem like it because it might look like, well, this is separate from all of those. If you actually calculate it, it's not, but it looks like it could be. I'm just telling you, I already calculated. It's not, but it looks like it might be. Sometimes there will be. And how would you interpret this data? Well, that's, like I said, you could say things like, well, men and women are really not the same. And they have different kinds of distributions. Specifically, I'm talking about now down in here. The men doesn't do this little weird deal where it was going down and then it went to zero, and then all of a sudden some averages showed up again at a higher pulse rate per minute. And then you can ask questions about that as far as how do you interpret that. And you might have to think about that a little bit. Why in the world would that happen with women and not with men? And the answer has to do with there's something women can do that men just can't do. And I'm going to leave it at that because I bet you can figure out what's going on with the group of women that's here. And if you think about it, there's a small number of women in the world that at any point in time are pregnant. That's what's going on here. When women are pregnant, they get a higher beats per minute because they need to pump more blood to the baby. Okay, so that's what's going on there. It's not 100% of women that are pregnant, so it's not surprising that it's a small number because at any moment, it's a small number of women in the world that are actually pregnant. Can you apply this interpretation to all? No, I would say there's always going to be exceptions to this kind of thing. So you got to be careful on what you use as assumptions. Can I assume that this applies to everything? No, but it gives you a pretty good, decent look at men in general will have lower, women in general will have higher, and women because of pregnancy have some differences going on down at this end. Okay, a specific kind, I already mentioned this, what's called the normal distribution. You might know this as the bell curve, but in statistics we're going to call it the normal distribution. In an algebra class, you would call it a Gaussian curve. Carl Gauss is the guy that came up with the equation that would actually model this curve. And it's the idea of when you're looking at this, does it kind of do this where it goes up and then kind of comes down basically, and I'm going to have that here. Frequency starts low, increases to one or two high frequencies, then decreases to a low frequency again. So it starts low, goes up, comes back down, and the distribution is approximately, please pay attention to this, it's approximately symmetric. Like this one's not. I put this one here on purpose. It's not a perfect bell curve. Okay, it skews off, is the term, more to the right than it does to the left. But I would still argue that this is approximately a normal curve. Okay, so you have to be a little bit flexible. If on, say, a test I give you something like this, similar to what we're looking at here, and I say, is this approximately a bell curve, or excuse me, I'll use the term normal. Is this approximately a normal distribution? I would want you to say yes. If I was asking you and it looked something like there was a big bunch of data and then a little bubble, kind of like with the women being pregnant kind of thing, I would say, well, maybe not. That one's probably a no as far as being a normal distribution because we had a maximum and then a secondary maximum that was just a much lower. And so I would maybe argue that one's no, it's not a normal distribution there. They should be roughly, again, this is a vague term, roughly a mirror image. So it doesn't have to be perfectly symmetric. Again, I picked this on purpose because I didn't want it to be perfectly, just approximately symmetric. All right. On page 58 and 59 of your textbook, there is a how to make a histogram on your Texas Instruments calculator. Sorry, if you have a Casio, you're going to have to go to Mr. YouTube. Again, with the calculator, you do not get to choose the number of classes. It does it for you. So it's quick and easy, but at the same time, you're missing out on some of the control. You do have to use some data from Appendix B for some of your problems. This is on page 769. Please take a look at these. Again, I wouldn't say you need to do them all. You should make sure you do enough of each kind. There's just some different kinds of questions. Do one or two of each kind until you're comfortable enough to say, yeah, I got this. Once you feel that, move on to a different kind of question. Okay, but please practice what's there. You just don't necessarily need to do all of them. Have a good day.